Sorry, can I ask a question about the previous talk?
Yeah, sure. Yeah, while we're waiting. Yeah.
Yeah. So you defined this field psi in the end, right?
Can you say again, please?
So you defined this field, sorry, not the field, a state psi
Yes.
at the very end of the lecture, while trying to discuss this.
Here?
Yeah, before this. Yeah, exactly. This psi.
Yeah.
So that is a very special state, right? I mean, I understand that from the expectation value of the density matrix that you calculated.
This is not a very special state. This is a generic state. Sorry, this state.
Yeah, but yes, exactly.
It's an extremely generic state. You see, I've chosen a basis.
Mm-hmm.
You see, so maybe you're talking about this state being a special state because you're saying the coefficients are 1 or something. Yeah, but remember. Good, but it's not a very special state because what we're saying is that pick a generic state in the big space. When you pick a generic state in the big space, you will find that the eigenvalues of the density matrix are all close to 1. Then once you've done that, then you can pick a basis so that the state looks like it does on the board. So
So I understand that that the average of these eigenvalues will be close to 1 or whatever, 1 by e to the power s prime by 2, and that's why
the fluctuations will also be small. We also proved that. It's not just that
it will be. The deviations will be small, but it will not be non-zero, right? So the proof that follows this.
You could put something like this. You mean?
Yeah.
Yeah, you could put 1 plus or minus epsilon, where epsilon is very small, and you can.
And epsilon depends on m.
Epsilon depends on. Yeah, m. Fine. It depends on m, but epsilon m is small everywhere.
Yes, but then the proof that follows this. I mean, when you're trying to prove that for every a you can find a tilde.
Yeah.
That requires all these coefficients to be exactly same, right?
No, it's only if you want the answer to be finally 2 root 2 exactly that you want. You see, somewhere here we proved this. Yeah, here. In general, this would be 2 root 2 plus order epsilon, where epsilon is some average size, right, of the deviation.
Oh, okay.
So to get 2 root 2 exactly, you're right. We need everything to be exactly 1. But the point is that if you don't want everything, you don't want to get maximal violation of Bell's inequalities. You're happy.
I just want it to be greater than 2. That's what.
Exactly. You just want it to be greater than 2. So whether it's 2 point, if it's 2.8, we are already happy, right? Or it'll be much more than 2.8. It'll be this order epsilon. This epsilon size of fluctuation is very small, right? So it's So it'll be we can make it very small because once the size of the two Hilbert spaces is very big, these fluctuations get very rapidly damped.
Right. So the idea is that even for those states, like for which the coefficients are 1 plus this epsilon m, even for them and for these operators a, I can construct a tilde. It's just that the form will not be as simple as the one you have mentioned. Is that correct?
Actually, I think you could take the same a tilde and you would just find that instead of 2 root 2, you'd get 2 root 2 plus order epsilon.
Yeah. But I'm saying I can also find some a tildes for which it will be exactly 2 root 2, right? Like I can find the maximal entanglement.
Maybe, or you may not be able to find it, right? It may depend. Like you can't always find something which is maximally entangled. So it'll depend a little bit on what was the operator you started with. I mean, if you have less than maximal entanglement on the two sides, it might still be the case that some operators on one side are entangled. But if you started with some choice of A1, A2, maybe that A1, A2 is not.
But isn't the assumption that for every operator that I define on the smaller subsystem, I can always find an operator in the larger subsystem for which it's maximally entangled?
Well, okay. If you always no, that's not necessary. Because this operator A1, A2 in the smaller system may be entangled with something else that's also in the smaller system. So it's not necessary that you can always find the partner is always living in the bigger system. It is true that for generic states, the partner is living in the big system. And for generic states, the partner is almost entirely living in the big system, maybe not exactly.
Okay.
But you see, the partner could also be living in the same system.
But it'll never happen that that the partner will entirely live on the smaller system.
It's not it'll never happen. Of course, it'll sometimes happen because this is
I mean, for atypical states may happen, but generically it'll not happen.
Exactly.
Okay. Yeah. Thanks. Thank you.
Okay. Thank you. Okay. Great. So thank you for the question. I think maybe we can start the lecture if there are no further questions. Okay, so welcome everyone to another week. We are actually today going to discuss a pretty interesting topic, which is going to be the second major paradox that we are going to arrive at. And this paradox is sometimes called the monogamy paradox. Okay. This paradox was formulated first by Mathur in 2009. So it's now, maybe 12 years old. But after that, there was a lot of activity on this paradox from the time of the AMPS paper and later. And I think this paradox is actually, in the end, I'm going to try and argue there's a resolution to the paradox, but I think the paradox is still very interesting because it really forces us to think about issues of quantum information and quantum gravity. And it's really, in some sense, been pretty important for many developments that have happened in black hole information and also in general in quantum information and quantum gravity in the past 10 years or so. So the idea of the monogamy paradox is actually extremely simple. It's so simple that we can state it in 3 lines. And the idea is actually the following. It's that, first, that the modes across horizon are entangled. So this is one. Then secondly, for an old black hole, near horizon modes are entangled with far away modes. And if you just look at the 2 things I've written on the board, you will see, they're immediately in contradiction with what we've been saying about entanglement and the monogamy of entanglement. And this contradicts the monogamy of entanglement. Okay. So this is pretty simple to write down. And in fact, the words are so simple that you could also write this down in a popular description. But in fact, we are going to spend the entire lecture trying to make this precise, trying to make all of these things precise. So we are first going to make this part precise, then we're going to make this part precise. And once we do that, we will immediately come into some contradiction with C. And the reason to try and do this in perhaps some of you might think more detail than is required is because there's been so much discussion on this paradox and there's still so many papers that are written on this paradox. It's important for us to be able to at least tie up those loose ends that can be tied up. And that's the reason we are going to spend some effort in doing this and rephrase this in terms of Bell correlators and so on. I should also say that much of the literature and the way the paradox was originally formulated was not in terms of Bell correlators, which is how we will formulate it, or not in terms of CHSH correlators, but in terms of the von Neumann entropy. As I explained a few lectures earlier, the von Neumann entropy has a slight disadvantage in that it has, it's a UV divergent quantity. And so there are every now and then questions raised about, whether those UV divergences somehow matter. And I'm going to try and argue that those UV divergences are not significant. And one way to, set aside those issues of UV divergences and regulators and focus on the essential physics is to look at CHSH correlators, which can be computed in effective field theory. So while we go ahead in this paradox, I'm going to try and point out which of these things, which of these points on the board we can make precise within effective field theory and where the effective field theory intuition gets violated. So please try and keep a watch on that. But as I said, we are just basically going to slowly go through these points A, B, and C today. Okay? So let me start by just discussing entanglement across the horizon. Okay? So in fact, we already spent towards the beginning of this course a fair amount of time discussing how you have modes and degrees of freedom across any null surface, and in particular also across the black hole horizon, which are entangled with each other. So let me just remind you very quickly of what we did. We said on both sides of the horizon, if you have a horizon like this, you can define some modes. And the way you define the mode is you take a quantum field and you integrate the field with some function of the kind I've drawn on the board. In fact, this field is moving parallel to the horizon. These modes are moving parallel to the horizon. And these functions, remember, were labeled by a frequency and by an angular momentum. And so you could call these modes outside the horizon A omega L, and you could call these modes behind the horizon A tilde omega L. And both of these modes are supported very close to the horizon. And the way one should think of them is that they are right moving modes, right moving in the sense in which I've drawn them, that they're right in that they move parallel to the horizon. So they're right moving modes which live in the near horizon region. Okay, so it's quite important, and we spend some time trying to define these modes as local degrees of freedom. So these are not modes which are defined by taking the quantum field and integrating it everywhere all over the space, but just by integrating it in some region near the horizon. And so these give us a way of extracting local degrees of freedom. Okay. So now we wrote down some equations about these modes. Let me remind you what those equations were. We said that if you define these modes, then these modes, so the black hole, you're in some black hole state. This state is some, lives in some theory of quantum gravity. Maybe it's some string theory. It's some complicated state, but it's still some state in the Hilbert space. And we said, these modes have to satisfy some relations. And the relations are that, if you act with A on one side, that's like acting with A tilde on the other side. And there's a similar relation, of course, for A tilde. So you could, which is that, okay. So this is equal to 0. Okay. Now, on the right-hand side, we actually never have exactly 0. It will never exactly be 0. So in fact, there are order epsilon corrections, since I was just asked about those corrections. Those order epsilon corrections come from the fact that these modes have compact support, and you can never actually make the right-hand side 0, but you can make it pretty small. And we discussed how you could make it pretty small by constructing these smearing functions and so on, and we won't go through that whole story again, but you can make it small. And effectively, for all purposes in this lecture, you can make things 0. And the reason, once again, as we discussed at the beginning in the question, the reason we don't care about these order epsilon corrections is that we are going to find at the end of this a paradox which is an order 1 paradox, and so these order epsilon corrections are not going to matter. Okay. Now, in particular, notice that the fact that you have these relations tells us that there are some correlation functions in the state between the modes A omega and A omega tilde. Okay. It tells us that there is some correlation, and you can work out what the correlation is. It turns out to be this. This is quite simple to derive. It just comes from the fact that A tilde omega is like A omega dagger with a factor of e to the minus beta omega by 2. And then A dagger gives you 1 by 1 minus e to the minus beta omega. And therefore, A tilde gives you e to the minus beta omega by 2 by 1 minus e to the minus beta omega. So I hope everyone understands this. And this is already almost in the form, in the kind of form that we need. Because remember when we spent last lecture discussing these CHSH correlators, we were talking about 2-point functions. And in front of us, we have a 2-point function of modes across the horizon. But this kind of 2-point function, we cannot immediately and directly insert into a Bell inequality or try and check if it violates Seidelson's bound. And the reason for that is that these operators are all, these are not bounded operators. Okay, so these don't have operator norm 1. And it was important for us, in all of these inequalities, that we have a way of normalizing the operators, and we look at operators which have eigenvalue plus or minus 1. And so we now want to extract some operators from these modes on opposite sides that do have operator norm 1, that are bounded operators, and which we can insert into Bell's inequalities and get a violation of the Bell inequality and get a violation of the maximal allowed classical correlators. Okay. Now the key point. Okay, I'm going to do some algebra maybe for half an hour or so, but let me just try and explain the key point. The key point is that these operators A and A tilde, remember they were defined by taking a quantum field and by integrating the quantum field with some smearing functions and so on. But in the end, they're just some simple harmonic degrees of freedom, right? So in the end, their behavior is quite simple. So even though they come from a quantum field, They're just simple harmonic degrees of freedom. And the idea is to exploit the fact that they're simple harmonic degrees of freedom that are entangled in a particular way. So we are going to do some algebra, but I want to emphasize that what we are doing actually is quite simple. And in fact, one of the reasons it seems unfamiliar is because, at least the way quantum field theory is taught, at least the way I learned it, maybe it was just me when I learned it first, it was something complicated about these infinite dimensional, these operators which acted, which were all continuous. And, we always talked about S matrices or products of fields or local operators. But in fact, fields, it's true, have an infinite number of degrees of freedom. But if you take a quantum field, you can also extract some simple degrees of freedom from it. And the main idea is to try and extract some simple harmonic degrees of freedom. Okay? Simple harmonic degrees of freedom, and use those simple harmonic degrees of freedom to violate Bell's inequalities. So, fields can be very complicated, and they can describe complicated processes, and, there are operator product expansions we can write with them. But they can also just describe simple countable Hilbert spaces. There are simple countable Hilbert spaces that are embedded inside field theories. And we're just going to focus on one of them. That's going to be the idea of what we're going to do. So we'll try and, I'll try and write things down more precisely. But the idea is very simple. And it might seem unfamiliar, but that's just because, it's so simple that you don't usually deal with it in QFT courses. Okay. So the first thing is that, given these operators, we can define the number operator. And the number operator is just this. Okay. And there's similarly a number operator you can define for these twiddle modes. And that's just this. Okay. And this number operator, let me remind you, is just a product of two field operators. Okay, so every time we are writing these things, you can remember that, these A's and A tildes are smeared fields. And so this number operator is a product of two such operators. Okay. Now, given such a number operator, we can define a projector onto eigenvalues of this number operator. And in particular, I'll write down an equation, and then I'll explain what the equation is. I can write down this kind of an operator. Okay. This is a well-defined operator. It's an operator I can manipulate and I can do various things with. And this on the left-hand side is just notation. But if you think about what this operator that I've done on the right-hand side does, you see that if n omega L is equal to this small n, then this integral just becomes 1. Right? So I'm doing the integral from 0 to 2 pi. If n omega L is some integer and it's not equal to n, then of course this integral is just 0. Right? So this integral is only 1 in the situation when n omega L is equal to small n, and it's 0 otherwise. But notice that this operator n omega L that we have defined is just the number operator for some creation and annihilation operators. And therefore, we know from elementary quantum mechanics that its eigenvalues are integrally quantized. And therefore, this operator that we have is actually a projector onto one of these eigenvalues, and it projects onto this operator, which is nn. Okay? Now, on the left-hand side, the notation that I've used is a bracket notation. It's a notation which says, ket n bra n. But I want to emphasize that the Hilbert space we are looking at is actually the Hilbert space of the full black hole. Okay? So there is a black hole which lives in a very complicated Hilbert space, which we don't actually know how to describe. And, there might be all sorts of complications and subtleties in that Hilbert space. And so on the left-hand side, what I have is just notation, which is meant to remind you that what we are doing is that in this ultra complicated black hole Hilbert space, we are choosing to focus on a simple harmonic degree of freedom. And we have a projector onto the eigenvalue n for the simple harmonic degree of freedom. Whenever you see the operator nn appear, you should think of the expression on the right-hand side, which is an expression which is well defined in effective field theory. Okay? So the precise definition is always on the right-hand side, and the left-hand side is just notation, and it's suggestive notation. But remember, we are not in the Hilbert space really of one harmonic oscillator. We are trying to use this operator on the right-hand side to mock up such a Hilbert space in a big, complicated black hole Hilbert space. Okay. Similarly, just like we can define this kind of an operator, I can also define an operator. Before I go on to that, Let me point out that, the operators that we defined, some of you might worry that, maybe there are interactions that turn on. So in particular, there might be gravitational interactions that turn on. And when we turn on gravitational interactions, the commutators and so on that we computed might not be exactly correct. And it might happen that in the presence of interactions, n omega L does not have exactly quantized eigenvalues. Okay. And that's okay, because, even if it's not exactly quantized, you see that this projector still gives us something that's pretty close to 1 when n omega L is close to n. If the eigenvalues of n omega L get shifted, and they get shifted perturbatively by some term which, you would expect by dimensional analysis, looks like 1 plus omega by Planck scale. So, omega that we're going to look at is going to be of the order of the black hole temperature. So this is an extremely small term. So even if the eigenvalues of n omega L are not exactly integrally quantized, that will mean that what we have here is not exactly a projector. It doesn't exactly give us 1 and doesn't exactly give us 0 for the other cases. But the nice part of everything we're going to do, which I emphasized also, I guess, in the answer at the beginning, is that, to every equation that we write down here, you could always add order epsilon corrections, and those order epsilon corrections would not change the final contradiction that we are going to get. Okay? And this may add order epsilon corrections, where epsilon is a small parameter that, as I said, naturally would be omega or m Planck, but it's not going to actually affect the final conclusion. Okay, so every equation we write down, you should feel free to add order epsilon terms. Are we in some kind of a Fock space then? Yeah, there's a question which asks if you're in some kind of a Fock space. We are not in any kind of a Fock space. There's no assumption that the full black hole lives in a Fock space. There's no such assumption here. As I said, what we have on the right-hand side is a quantum field operator, which is well defined. This n omega L is just a product of two fields. I put it inside an exponential. I did this, and then I did this integral. So this is something you can manipulate. You can compute various things with. The full Hilbert space may not be a Fock space, and the whole point is to try and mock up something that looks like a simple harmonic oscillator space within a complicated space. So the whole, one thing which will keep coming up again and again is that it's often useful to look at a little Hilbert space. You have a big Hilbert space, but within that you can find smaller and simpler Hilbert spaces, and this is one example of what we are doing here. Okay? What we're doing here constitutes one example of such a situation, of such a technique. Okay, now just like I defined this operator nn, I can also define the operator nn plus 1. And I emphasize that this is also just notation. What does this operator actually mean? What it means is I take this operator nn and I multiply it with a omega L. Okay, and when I write nn, once again, this is notation. And what I really mean is you should insert this. Okay, so this operator, which is n into n plus 1, also has a definition entirely in terms of quantum fields. And the definition is just that you take nn, you substitute it from here, and then you multiply it with another factor of a omega L. And this a omega L is just a field which is smeared with something else. So this n into n plus 1 is also a well-defined operator within effective field theory. And similarly, I can define an operator which is n plus 1 into n. And this operator is 1 over... Oh, sorry, I made a mistake with my normalization. Should be n plus 1. And this operator is n plus 1 and a omega L dagger into nn. It should have been n plus 1 because these two operators I've written on the bottom two slides are Hermitian conjugates of each other, and a dagger always gives you square root n plus 1 into n plus 1. So this operator now is correctly normalized the way I've written it, with the 1 over square root n plus 1. Again, I emphasize that this operator on the last line also has a concrete expression in terms of fields. Okay. Now, just like I defined these operators, I can also define the operator n tilde, which is this, which is the same expression, but just in terms of this operator. Okay. And I'm going to use this notation, which is n tilde, but remember the eigenvalue is actually n. Okay. So this is actually the operator. This is the projector onto those states which have eigenvalue n, but the states are the n tilde states. Okay. So the states are defined with respect to these tilde modes, but they still have eigenvalue n. So this n tilde is not a different number. N is the number, and the tilde is just there to distinguish the operator from nn. Okay, so that's the notation we're using. Maybe it's suboptimal, but we'll just stick with this notation, and please don't get confused. Remember, the eigenvalue is n, and the tilde just differentiates the eigenstate from the state of the n omega L operators. Okay, and just like this, just like we did previously, we can define the operators n tilde into n tilde plus 1 and n tilde plus 1 into n tilde. So once again, these operators are defined exactly the way we defined them previously. Right? This is like 1 over square root n plus 1 into n tilde, but this time multiplied with an a tilde. Okay, and this is the same expression, but this time multiplied with an a tilde omega L dagger. Okay. The reason I'm going through this in detail once again, as I said, is just to make sure that we've dotted all I's and crossed all our T's. But these are well-defined operators we can define. Okay, now that this is done, I can now start summing over these operators. You see, I can start taking linear combinations of these operators. And it's very convenient to take the following kind of linear combination, which we will now do. So I'm going to define an operator, which I will call A1. And you see already, this is the operator that's going to go into this CHSH inequality. And the operator is defined as the following sum. So let me just say what this operator is doing in words. I'm summing over n equal to 0 to infinity over these integers. The reason and every point I write down one of these operators, I remind you, it's actually defined in terms of the field on top. And I'm summing over, these operators are defined with respect to different integers. And I'm summing over these integers from 0 to infinity. And what I'm doing is I look at the projector onto odd eigenvalues, and I subtract off the projectors onto even eigenvalues. Okay, so it's some kind of sum over like all the set of eigenvalues that I have for this n omega L. And similarly, I'm going to define an operator A2, which is also a sum from 0 to infinity, but it does something slightly different. Okay? It moves us from the eigenvalue which has 2n plus 1 to 2n, or it moves us from the eigenvalue which is 2n to 2n plus 1. Okay, let me try and give you a little bit of intuition for how you should think about these operators. The way you should think about these operators is think of a single simple harmonic oscillator. I tried to say that we are not in a Fock space and so on, but just to get intuition, think of a single simple harmonic oscillator. And in this simple harmonic oscillator, we have a lot of energy, we have a lot of levels. There are a lot of number levels. And there are odd levels and there are even levels. And what these operators are doing is you have clubbed up the levels into two. So you have clubbed up odd and even, odd and even, odd and even. And then if you think of what these operators A1 and A2 are doing, they are behaving like sigma Z and like sigma X on these levels of 2. Okay. So just to say this more clearly, once more, you clubbed up all these eigenstates, all these number eigenstates of this oscillator into pairs of 2, and then within each pair you have these block diagonal kind of operators which behave like sigma Z and sigma X within each pair, and then you've just summed over all of them. Okay, so that's all these operators are doing. So they're pretty simple operators, even though they look complicated. And if you were to write them down in terms of fields, it would look like there's an infinite sum and so on. But in fact, these operators are doing something quite simple. The other thing I should say is that there are sums here which are running from 0 to infinity, and some of you might be worried about those. But as we will see, in fact, the higher terms in the sum will never matter. And if you decided to sum from n equal to 0 to 10, in fact, if you even decided to sum from n equal to 0 to 2, we would still be in a position to get a paradox at the end of this lecture. Okay. Very good. So far, so good. Now, let me just point out, just say a little bit more formally. You see, we can also compute this operator A1 and we can square it within effective field theory. Okay? So if you square it, what happens? If you square it, you see, we just have some projectors and we need to square those projectors. Okay? So let me just remind you how this looks like. And then So I'm just squaring A1, and because A1 is a sum over n, I took one expression and I multiplied it with another such expression. And the only thing we actually need here is the fact that when you multiply two of these projectors together, you get back the projector if the two terms are the same, and otherwise you don't. Okay? And this is a pretty simple expression, and this we can prove with an effective field theory. Right? This is just saying that you have these operators which are simple harmonic oscillators. You have these projectors. You multiply two of them, and this is what you will get. It doesn't, and once again, it may not be exactly true in the theory of gravity, but there'll be order epsilon corrections which don't count for us. And therefore, you see in this sum above, the only terms that contribute are the ones where this one contracts with this one, and where this one contracts with this one. And therefore, notice the minus signs in the middle actually get cancelled out. And so you get from here simply sum over n into 2n plus 1, 2n plus 1, and plus 2n, 2n. And so now we just have a projector over all eigenvalues, and this is just 1. Okay. So A1 is an operator which has the property that it squares to 1. And I won't do this in detail, but it's quite easy to check that A2 has the same property. Okay. So A2 squared is also equal to 1. Okay. So both A1 and A2 are operators which look like they're complicated, but if you think of the intuition I gave you at the beginning, where you think of them as sigma z and sigma x acting in this simple harmonic oscillator space, we'll see that A1 squared and A2 squared are 1, and it's natural that all their eigenvalues are basically plus or minus 1 and nothing else. Okay, good. So far so good. Are there any questions about this, about the operators that we are defining?
So these are not like projection operators in usual quantum mechanics because they square to themselves, right? I mean,
A1 is not a projection operator. 2n to n is a projection operator. Okay. A1 is a sum over a lot of these things. So A1 is you have some things which come with a plus sign, some things which come with a minus sign, and so on.
NN is the projector operator.
Yeah. NN is a projection operator.
Okay.
And that you see. Okay. Very good. So now let me point out. We can also work out. Let me just say one more thing for future reference. You see, we can also work out what A1, A2 is. And if you work out what A1, A2 is, you will find that this just looks following. This just came from, multiplying the expressions that we had for A1 and A2. If you multiply them together, you will find this. But if you work out, on the other hand, what A2, A1 is, you will find that it gives you, the 2n to n plus 1 with a plus sign, and it gives you the other term with a minus sign. Okay? So these two expressions we have, I'm just doing some trivial algebra. You can check this on your own, but it's pretty simple. You just multiply them, you'll see this. But notice that the minus sign is in the opposite place. Here the 2n into 2n plus 1 appears with a minus sign, and here it appears with a plus sign. And therefore, these operators anti-commute with each other. Okay? So they have the property that A1, A2 is equal to 0. And in particular, that means that A1 plus A2, the whole squared, is equal to 2. Okay? So at some point, last lecture, we defined these operators that we called pseudospin operators. These are the operators that we wanted. We wanted operators which have the property that A1 squared is 1, is A2 squared, and A1 plus A2 squared is equal to 2. There were some questions last time, I remember, about whether these are reasonable operators to think about. Let's say you have some continuous, let's say you have some quantum field theory, or you have something else. Could you ever find such operators? And what we have in front of us right now are operators which are defined in a quantum field theory. We are using this notation which reminds us of the simple harmonic oscillator, but these are really operators which are defined using quantum fields. And we are saying that even in a quantum field theory, it is possible to find these simple pseudospin operators that basically behave for all effects and purposes like sigma z and like sigma x. Okay. So these are there's pseudospin operators as we define them. Okay, good. So now we want to compute some correlators with these operators. So that's the next thing that we need to do. Okay. So in particular, we need to compute these the correlator we want to compute is, we are in some black hole state and we want to compute the correlators psi A1 tilde psi and maybe A1 A2 tilde psi. Now, in fact, as I've been emphasizing, all of these correlators are things you could just compute in effective field theory. A1 and A1 tilde have some concrete expressions in terms of quantum fields. You could insert it. You could look at the 2-point function of the quantum fields and you could compute these correlators. This is an exercise that can be done. It's a tedious exercise, but it can be done, and and it will give you the expected answer. But we don't want to do this very tedious exercise. I'm instead going to take a slight shortcut and tell you how one can evaluate correlators of this kind, and that is by thinking of the fact, by defining some kind of density matrix that allows us to trace out all the other degrees of freedom in the black hole. And once again, I emphasize this density matrix is going to be an approximate density matrix, but I just want to explain how one can compute correlators of this kind, which we will need for the CHSH inequality. Okay, so let me just go back to the expressions we had for these operators n and n tilde, and let me remind you, let's say we have this black hole state psi, right? And let's say I act on it with the operator n tilde, which is a well-defined operation to do. So how does this act? Okay, so this, remember, n tilde is just a omega L into a omega tilde psi. But remember that we know how a tilde omega L acts on psi, right? We can convert that into a tilde omega L dagger, into a omega L dagger, into psi, into e to the minus beta omega by 2. Okay? I hope the step from here to here is clear. Okay? What I've done is I've replaced this a omega L with an a dagger omega L using the rule that we have for the action of a tilde on the state being related to the action of a dagger on the state. Okay. Now we also know, when we define these modes, we also notice that they actually commute with each other. Okay, so that's because they're modes on opposite sides of the horizon and they're defined in a way that they're spatially separated. And so these modes commute with each other. And therefore this is just the same as a omega L dagger into a tilde omega L dagger on psi into e to the minus beta omega by 2. Right? I just took the a tilde omega L dagger and I moved it to the other side. This uses the commutator. But now this is pretty simple because now I can use the rule that I had for a tilde acting on the state, and I find that this is just a omega L dagger into a omega L into psi, and in fact the e to the minus beta omega by 2 cancels off exactly because the a tilde omega L dagger comes with an e to the plus beta omega by 2, and therefore this is actually just n omega L psi. So we find, if you look at the first step of this equation and the last step, that n omega tilde on psi, or n tilde omega L, sorry, n tilde omega L on psi is the same as n omega L on psi. And you can check that this equation actually holds if you look at higher powers as well. Okay? So that tells you, and I emphasize that, when I say higher powers, I mean that Q is greater than 1, but Q can be larger than 1, but Q may be large. It doesn't have to be large, but it may be large. But Q is still order 1. So I'm never going to insert like S insertions or something. I just want to compute maybe up to 10 correlators. And you can check just by using the rules that we have for these A's and A tildes that this relation is not only true for N acting on the state psi, it's also true for n to the power q acting on the state psi. Okay? Therefore, it's actually convenient to think of this entire state psi, right, as actually, it's convenient, and I'll write a tilde because I don't want to assume any kind of factorization. It's convenient to think of this entire state psi as a state where n and n tilde eigenvalues are actually correlated. And in principle, it could be that they are entangled with the other degrees of freedom in some way. But notice that when you use the fact that A on the state is the same as A tilde on the state up to a dagger, you can check that in fact the state has to be nothing but e to the minus beta omega n by 2 into n tilde, okay, sum over n, multiply with the 1 minus, here I'm just doing a normalization. Okay. Okay. The reason I write a tilde here is because I want to emphasize that I'm not assuming that the state factorizes in some exact way into these 2 degrees of freedom and into the rest of the Hilbert space. I don't need to assume such a factorization. All I'm saying is that for the purposes of computing simple correlators of these A's and A tildes, only for the purposes of computing these simple correlators, I can compute these simple correlators by either using this state or by using an effective density matrix, which just looks like this thing I have here. Okay. Now, I want to emphasize that this is just an effective density matrix. And all I'm saying is that for the purposes of computing simple correlators, I can compute simple correlators using either the state on top or using this effective density matrix. So in fact, even when we discussed, Hawking's original paradox, I emphasized that it was important that, none of the results we have is exact. And, we should be quite careful that there could be order e to the minus s by 2 corrections, or there could be, corrections about maybe this doesn't work when you go to very high values of n and so on. And all that is true. Okay. So this is an approximate statement. I want to emphasize. Okay. This is an approximate statement. And I only want to use it, which is useful for computing correlators, useful for computing simple correlators. Okay. Okay. I hope this part is clear. The fact that we have these 2-point functions allows us to compute simple correlators by using this state as a shortcut. If you don't want to use this state, you can actually just go back to the quantum fields, as I said, and just compute the 2-point functions by brute force in the state psi, and just use the 2-point position space, 2-point function to compute those 2-point functions if you're going to compute. But this is just a shortcut. And as I said, it's an approximate statement. And if you're worried about issues of factorization or what happens and whether this density matrix is exact, you shouldn't be, because we are just using it as a shortcut. Okay. I hope this is clear. And if there are any questions, this might be a good part to take them.
Actually, there's one question asking, what does psi rest mean?
So psi rest, that's why I wrote a tilde here. Psi rest means the rest of the degrees of freedom. Okay. So please note, this is not an equality. This is just maybe this is actually an equality here, in that there's a sense in which you can speak of the density matrix when it's restricted to operators, the n and n tilde omega, and a and a dagger, and a tilde and a tilde dagger. So you can define a density matrix for those operators for computing simple correlators. The notion of this state is imprecise, and this is not an equality. And psi rest is meant to indicate that I'm focusing on these 2 degrees of freedom, which are near horizon degrees of freedom on opposite sides of the horizon, one outside the horizon, one on the other side. And there's a lot of other stuff in the world, and that's going into psi rest. Okay. But as the question correctly points out, we don't know what psi rest is, and we don't know if such a factorization holds exactly. And so that's why this is not an equality. But the precise statement is that you can use this kind of a density matrix as an approximate tool for computing simple correlators. Okay, that's a precise statement, and that's a true statement. Okay, I hope that answers the question. Okay, good.
I also have a question. What do you mean with the fact that it's approximate? The Hilbert space be approximately factorized? I don't really understand. It seems like it's either factorized or it's not. So I wonder what's the approximate mean in this setting?
Yeah, the approximate means actually the following. It means that if you take trace of rho effective, the precise statement is the following: O, where O is a so let me say the full. Yeah, let me explain what approximate is, and let me write down an equation. Okay. So let's say you compute O, where O is a simple operator made up of a omega L, a tilde omega L, a omega L dagger, and a omega L tilde dagger. Okay, so that's a pretty clear thing. Let's say I compute such an expectation value, then this is equal to trace in row effective of the same operator O, okay, plus order epsilon. So that's the precise statement. The precise statement is for the purposes of computing and a correlation function of simple operators, you could use this effective density matrix as a way to compute them, and that's all we're going to use. Okay, so this is the precise equation, and this is all we're going to say. So everything I said about factorization and so on is just for intuition. It's a way of thinking about it. But you're right that the Hilbert space doesn't exactly factorize, and all I want to use is the equation that's written here, and this equation is a true equation.
Okay, so thanks. That clarifies it.
Yeah. Okay. Thank you. Okay. Great. So let's use this equation and compute some simple correlators of these O's. So in particular, let's take A1 and A1 tilde on psi, okay? And you can compute what this is. Okay? So let me just remind you, we have this A1 has some expression in terms of twice A1, in terms of some sum. Okay? And now I have to take a direct product because these things acting in like the commuting operators. And now if you think about, this effective density matrix, if you think about this equation that we have on top, you will see that the only terms that will click are the terms where this one goes with this one and this one goes with this one, because the eigenvalues of n and n tilde are correlated. That's the first thing we proved. This density matrix is like diagonal in the eigenvalues of n and n tilde, and therefore, only this and this click and only this and this click. But once this and this click, then you'll just have a sum over the identity, and therefore this is just the same as psi into sum. I mean, this is just the same. This is just basically 1. Okay. I hope the 1 is clear. I can explain in more detail, but let me just explain where the 1 comes from. It comes from the fact that this clicks with this clicks with this, and then you're just left with a sum over projectors. Once again, 2n plus 1, 2n plus 1, and 2n, 2n. And that's just 1 by the logic that we gave in the beginning. Okay, so if you take this density matrix and you compute psi into A1, A1 tilde, you will find that it's 1. Okay, very good. This is good, but now we can compute something slightly more complicated. We can compute A2 into A2 tilde. And once again, you could compute this in effective field theory, but we'll use our shortcut to compute it. Let me just remind you what this A2 and A2 tilde were. 2n plus 1, this was 2n, and this was 2n into 2n plus 1. Okay. And then this A2 tilde looked like 2n twiddle plus 1 into 2n twiddle. Okay. Now, if you see what this does for you, notice that this 2n, if you project onto something which has 2n plus 1, okay, then which has, where the eigenvalue of the n tilde operator is odd, you cannot also try and project onto something where the eigenvalue of the n operator is even. Okay, and similarly, this way. Okay, so therefore, this just becomes into 2n plus 1, 2n tilde plus 1 into 2n, 2n tilde, okay, plus 2n, 2n tilde into 2n plus 1, 2n tilde plus 1 by the logic I just gave right now. The other terms cancel. In principle, you could have got 4 terms, but if you expand it out, you will see that 2 of those terms cancel, and therefore you're just left with 2 terms in the end. And this is then something pretty simple. You see, this is a correlator that one could compute in effective field theory, but we can use our density matrix to compute them, and this will turn out to be the following thing. It will turn out to be 2, and remember what is happening here is, you're selecting the 2n, 2n tilde state on the right-hand side. Just see what is happening here. You select the 2n, 2n tilde state on the right-hand side, and you select the 2n plus 1, 2n plus 1 tilde state on the left-hand side. Okay? So you pick up the coefficient of the 2n, 2n tilde state on the right-hand side, and you pick up the coefficient of the odd state on the left-hand side, and the same here. Okay? So this is actually just 2 into e to the beta into 2n plus 1 omega by 2 into beta into 2n omega by 2, and you sum over n, and you multiply the whole thing by 1 minus e to the minus beta omega. Okay. I hope the way I went from the second last line to the last line is clear. Let me just say once again, the way I did this was by using this density matrix, which was a shortcut to compute correlators of precisely this kind. When you insert this operator that you have within that density matrix, you will find that from the right hand side, you pick up the coefficient of the even term, which is this term. This is the coefficient of the even term from the state. On the left hand side, you pick up the coefficient of the odd term. Remember, this is the coefficient of the odd term in the state that we have. There's a factor of 2. This factor of 2 comes because we add this, and they are both the same. And then there's a sum over n. There should have been a sum over n on top as well, which has suddenly appeared. So let me reinsert the sum over n on top as well. Okay. And there's a sum over n, which was just carried from top. It did not magically appear. Okay. And then there's a factor of 1 minus e to the minus beta omega, which just came from the normalization of the density matrix. The density matrix had to be normalized, and that just came from here. Okay. So now after this is just some sum in doing like simple geometric series sums. Someone like me would almost certainly get it wrong. If I was to do it, I would probably get some, but Mathematica is good at doing simple things like this. When I was younger, I could also sum these simple series. And when we do this, you will find the following answer. Okay, you have to be a little careful about the algebra and about summing these geometric series. You're summing e to the 4n plus 1 over 2. And you have to be careful about the sum. But it's a trivial sum. And in the end, you get this expression. Okay. Okay. So we're almost done. Is there a question?
Just a quick question. Where does the factor of 2 come from?
The factor of 2 came from the fact that we had the two terms here, one here and one here, and they both give the same contribution. You see, in the beginning, we had A2 tilde, which would have had 4 terms. We got 2 terms, and then those 2 terms gave us the same contribution. That's why you got the factor of 2. Because you see, this one picks up the odd one from the right and the even one from the left. This one picks up the even one from the right and the odd one from the left. So, you know, but yeah, that's why you get
Thank you.
Okay, great. So now we're actually almost done. Now I'm just going to insert this in the CHSH correlator, and we'll see immediately a violation of the Bell inequality. You see, let's define B1 as cos theta into A1 tilde plus sine theta into A2 tilde. Okay, and let's define B2 as cos theta into A1 tilde minus sine theta into A2 tilde. You can check from the properties that we proved for A1 tilde and for A2 tilde that B1 squared is equal to B2 squared is equal to 1. Okay? And this is because A1 tilde, A2 tilde is equal to 0, and because A1 tilde squared is equal to A2 tilde squared is equal to 1. Okay? And once we have done this, we can just define CAB as being A1 into B1 plus B2, our usual CHSH operator, plus A2 into B1 minus B2. Okay? And we are allowed to insert these operators A1, A2, B1, and B2 into the CHSH operator because we've been very careful to ensure that they're all normalized correctly. And that's one of the reasons we went through this entire song and dance to make sure we have these operators that are normalized correctly and that have the right correlation functions. And once we do this, we compute now the expectation value of CAB. In fact, we have computed all the terms in this expectation value because we computed the A1 tilde terms. This, notice, is just cos theta into psi into A1 tilde psi. And it's sine theta into psi A2 tilde psi. Okay? The fact that you get a factor of 2 here is because you know, you have a B1 plus B2 and a B1 minus B2. When you add a B1 plus B2, you get twice cos theta A tilde. And when you do a B1 minus B2, you get a twice sine theta A2 tilde. And therefore, you get a cross correlator with an A1 and an A1 tilde and an A2 and an A2 tilde. And then there are these multiplying factors of cos theta and sine theta. We computed all of these correlators. So I'll just write down what the answer is. The first one is just 1. And the second one is what we just computed right now. and that is given by this. So this is the answer for the CHSH correlator that we have at the bottom. Okay, so this is the important answer. So the whole objective of doing this was to get this answer that we have at the bottom. Okay. Okay. Now, this is an answer which works. This is an answer which is telling us about the CHSH correlator of an operator which is on one side of the horizon. The A1 is outside the horizon and the B1 is on the other side of the horizon. It's like a bell correlator. But this correlator depends on a value of theta. This theta is not some physical thing. It's something that we inserted into the definition of the operator. Because we inserted it into the definition of the operator, we can choose theta according to our convenience and get the maximal possible violation of Bell's inequalities that we want. And you can see that this expectation value, oops, let me just copy this, well, let me just write down. We can see that you can check easily that this expectation value, okay, is max at tan theta is just twice e to the minus beta omega by 2 into 1 plus e to the minus beta omega. Let me just maybe copy it so you can see why that's the case. Okay. So this was the general expression we had for the expectation value. And you can see that this is maximized, just by simple calculus when tan theta is what I have written on top. And at the maximum, there's some simple algebra once more that one needs to do. But this is the last part. You find that it's this. The maximum value is given by 1 plus 6 e to the minus beta omega plus e to the minus 2 beta omega to the power half. Okay. So this is the maximum violation that we can get for, this is the maximum value of the CHSH correlator that we can get with the operators that we have defined. You could try and define other operators and do better than this, but this is already sufficient for us. And the reason this is sufficient for us is that if you stare at this expression for a few minutes, or for less than a few minutes, for a few seconds, you will notice that this expression is always larger than 2. It's always larger than 2. And the reason it's always larger than 2 is because you see there's a factor of 2 that's just sitting up here. Right? So the only thing we need to determine is whether this factor is larger than 1 or not. And the simple way to see that this factor is always larger than 1 is to square it. And if you square it, you will find that this is just 1 plus e to the minus 2 beta omega plus 2 into e to the minus beta omega. Compare it with what we have on top. You have an e to the minus 2 beta omega. You have an e to the minus 2 beta omega here. You have a 1. You have a 1 here. But now instead of a 6 e to the minus beta omega, you have only a 2 e to the minus beta omega. And therefore, it's clear that the numerator is larger than the denominator. And therefore, this factor is always larger than 1. And so you see that, you have a violation of the Bell inequality. And this correlator is larger than 2. Okay. So very good. You can check also that in the situation when e to the minus beta omega becomes close to 1, okay, in that situation, this is just, this is just 2. And this becomes 8 because you get a 1 plus a 6. So this, if e to the minus beta omega is, if as it tends to 1, the expectation value tends to 2 root 2, which is the max. And that happens because this thing in the square root becomes an 8 and the prefactor just becomes a 1. And so in the limit, in this limit, this becomes 2 root 2. But we don't actually care about the 2 root 2. It's always order larger than 2 by order 1. Okay. Okay. So we did a long thing to prove a very simple result. And the simple result is that the correlators, we can find correlators across the horizon, okay, or we can define CHSH operators across the horizon that violate the Bell inequalities, okay. Okay. Or that display entanglement. Okay. So this part is very robust. And I want to emphasize how robust this is when we come to the issue of firewalls and fuzzballs, which should now appear soon. And so, we spent a lot of time, we spent almost an hour in trying to very carefully define these operators using quantum field theory, using effective field theory, and we found that it display entanglement. Okay, so that part is good. This is step one of what we wanted to do. We have shown that there is entanglement across the horizon in a precise sense, and the precise sense is that you compute Bell correlators across the horizon, and you find that it's larger than 2. Okay. So in some sense, it was kind of an intuitive result. It's the result that many of us have just heard, because people just say it all the time. There's entanglement across the horizon. There's entanglement across the horizon, and there is. But we just, what we've shown right now is that you can define it and measure this entanglement very precisely in terms of simple correlators of field operators on opposite sides. You need to do a little bit of work to make these field operators bounded, but in the end, you can find the CHSH correlator, which is larger than the maximum allowed classical value. Okay, before I go on to the second part, which is defining entanglement of operators nearby and operators far away, are there any questions about this part?
Yeah, I was. Oh, go ahead.
Yeah, in the computation of A2 tilde.
Yeah.
If you could take us to that slide. Yeah.
Here, yeah.
What happens to this 1 minus e⁻² minus beta omega part?
It is there. That's why I said you have to do the sum carefully. So there is a 1 minus e⁻² minus beta omega, but when you do the sum, it will cancel with something in the denominator.
Okay.
So the 1 minus e⁻² minus beta omega is there, and that's why I said you have to be a little bit careful with the sum. But if you do it you carefully, it will cancel, and you'll get a 1 plus e⁻² minus beta omega.
It's an infinite GP sum, right?
It's an infinite geometric progression, correct?
Thanks.
Yes. So you have to do it carefully, but you will find that it'll work out.
Okay.
It's not so hard to see it'll work out. But yeah, you could use, you can just do the sum.
Sure. Thank you.
Okay. Yeah. By the way, once again, to emphasize, we have all of these infinite sums here, but it's important that at some point you could decide to truncate the sum. You could say that, notice that as is common in all geometric progressions, the higher terms in the sum are not really giving you significant contributions. So you don't actually have to trust our correlators for the higher terms in the sum. We are happy if these correlators work for the lower terms in the sum. And that's enough for proving what we want to prove. Okay, great. So now, yeah.
Okay, yeah. No, I was just saying Prahar has a raised hand, so please go on.
Go on, please. Yeah, go on. Yeah.
Is the sum convergent, or do we have a missing sign? It looks like the ratio is greater than 1 in the infinite sum that you had in the previous slide.
Yeah, we do have a missing sign. Thank you. It's minus. Thank you very much. Yeah, you have a missing sign. It's always e⁻² minus beta, because all the coefficients, everything with higher n comes with smaller coefficient. Thank you for that correction. Yeah. Good. Are there any other questions?
The question about the physical origin of this entanglement, because
yes,
now we just took two random modes basically across our horizon. I can understand the entanglement if I think about the modes as coming from the vacuum, etc. But so far, I've not really thought about these modes in that way. So where does the entanglement come from?
They were not random modes across the horizon. I mean, they were defined by taking the field and integrating it with a particular, so they were modes where you took the field and you integrated it with a particular smearing function on the right-hand side, like something which was u to the I omega, and something else here, which was u to the minus I omega. So the smearing functions that we used to define these modes had some relation. So you take the field, you integrate it in one way to extract a mode A, and you integrate it in another way to extract the mode A tilde. And these modes are defined with respect to this omega and L. For instance, if you try to ask, is the entanglement between A omega L of 1 omega and A tilde omega L of a different omega, there would be no entanglement. So you're taking the field and you're integrating it in a particular way. So this entanglement is ultimately reflecting the fact that across the horizon, because the space-time is smooth, you're forced to have a certain level of entanglement. And it is coming from the fact that the space-time is smooth, and we are just saying that in the horizon, because the space-time is smooth, you can extract Bell pairs from opposite sides of the horizon. So that's what we have shown right now. Does that answer the question?
Yep, thanks.
Okay, thank you. Okay, great. Excellent. So now let's go back to the other part. In fact, the other part is technically simple. So now we need to go to the other part. So which was the part where we argued for entanglement between modes which are close to the horizon and modes which are far away. So let's draw again the Penrose diagram of the black hole. Okay, so this is our extended Penrose diagram in which we are thinking of this process happening. Here was some matter which came and which formed the black hole. Okay, so this is the horizon, and I hope this Penrose diagram is clear. So this is the matter. Okay. So there's some matter, some dust or something else that fell in. And now what I want to do is I want to focus on a Cauchy slice. Let me try and choose some other color. So I want to focus on some slice that runs through this geometry. And let me some slice that cuts through the late time part of the geometry. And that stays away everywhere from the singularity. So this kind of slice is sometimes called a nice slice. It's a nice slice in that it stays away from the singularity. And it provides it doesn't have anywhere any large curvatures or anything else that's happening, that's bad on the slice. And it's just a Cauchy slice for the geometry. So that, people use the word nice slice, but there's nothing to get intimidated about. It's just what I've drawn on the board. There's some black hole collapse, and then you just draw some Cauchy slice, which doesn't go close to the singularity and which captures some of the Hawking radiation or a lot of the Hawking radiation at late times. Okay, and now we can divide this slice into three parts. One part, which we'll call here, will be the part. Maybe I should use a different color. Will be the part behind the. What should I use? Screen. Okay, yeah, one part is the part behind the horizon, and I'll call that B. Okay, so I hope B is clear. It's the part behind the horizon, and then there is a part which is outside the horizon, which I'll call A, and then there is a part which is far away, which I'll call C. Okay. So I took this nice slice and I divided it into three parts. One which was just behind the horizon, one which was just outside the horizon, and one which was far away. Okay, so A is the region just outside. Okay. B is the region just inside, and C is the region far away. Okay. So I hope this division is clear. Okay. Okay. Now we are going to have to wave our hands a little bit. Okay. So we'll wave our hands, and I'm going to try and make some assumptions. And the assumptions are actually going to be sloppy, and they're going to be sloppy because that's the best anyone has done. But maybe if we wave our hands fast enough, we can try and believe them. Some of them are reasonable, and the others we can ask questions about. But I'm going to make two assumptions. Okay, the first assumption I'm going to make is that notice that the Hilbert space is a Hilbert space of a quantum field theory. Okay, maybe I can copy this diagram so it's always in front of you. Okay. So the Hilbert space is a Hilbert space of a quantum field theory. And so it's actually an infinite dimensional Hilbert space, right? It's not a finite dimensional Hilbert space. Okay, so just so you remember what these things are. So this is an infinite dimensional Hilbert space, but we'll argue that the dynamics can be formulated in an effective Hilbert space of size e to the s. Where S is the Bekenstein-Hawking entropy of the black hole. Okay, so this is SBH. And this is kind of, it's a reasonable assumption. In fact, it's a kind of assumption that we ourselves used previously. We really have, as in any quantum field theory, an infinite dimensional space. There are lots of degrees of freedom. But when we talk about black holes, we count the entropy of black holes, and we believe that entropy is telling us about some degeneracy. So that's the degeneracy we believe is SBH, and therefore if it is SBH, the size of the corresponding Hilbert space is e to the SBH. And so no one has ever done this precisely for a black hole in flat space, but we can say, well, okay, there are some set of states which are e to the SBH, and these are the set of states that we want to look at. If you're in, here we're not talking about large black holes in ADS, where the entropy has actually been counted in some examples in string theory. These are evaporating black holes, or these are small black holes in ADS, if you want to think of ADS. And so no one has ever done this precisely, but we believe that this should be doable. Okay, so this is I think a reasonable assumption. Then there's another assumption that we are going to need to make. And the other assumption we are going to need to make, which is an assumption that actually is very important to all of these arguments and all of these paradoxes, but in fact is an assumption which, if you look at the original papers on the subject, was not even stated explicitly because it seemed to be so obvious. The second assumption is, so let's call this Hilbert space H. Okay, so this is the Hilbert space H. The second assumption is that in this big Hilbert space H, we can find effectively some subfactors which look like HA and HB and HC. Okay? So the second assumption is that HA times HB times HC is a subset of this big Hilbert space. Okay, so the second assumption is that the Hilbert space effectively factorizes. Okay? In fact, I also said earlier in this lecture at some point that the Hilbert space effectively factorizes, and but there was a precise sense of what it meant for the Hilbert space to effectively factorize. Here, we'll see how strong this assumption is when we examine this a little bit later. But it's being used in the sense that whatever, in some sense, we know that the Hilbert space in gravity does not factorize, but we would like to assume that this is somehow not significant, or not a significant effect for what we are going to compute. And in fact, because the point at the end is going to be that there's an order 1 correction to some Bell correlator, the idea is that maybe it's true that the Hilbert space doesn't effectively factorize, but we somehow want to maybe it's true the Hilbert space doesn't exactly factorize, but we want to somehow wish away that fact and not deal with that complication and assume effectively that there are 3 subspaces. Okay? But this is an important assumption, and without this assumption, nothing else would work. And it's not always made explicit in the literature, and sometimes because people think it should be so obvious. In fact, this is the assumption that we are going to argue later is problematic, and it's the assumption that's going to fail. But for now, we'll just make it and see where it leads us. Okay. The other assumption, once we've said this, is that the modes. The next assumption is kind of simple, is that the modes A omega L and A omega L dagger, they act within this Hilbert space HA, within HA. And, these modes A tilde omega L and A tilde omega L dagger act within HB. Okay? So once we said that the Hilbert space factorizes, then, it's pretty clear that, let me remind you once again, so maybe I can just paste here again. Just so you keep track of what A, B, and C are, once we've said that the Hilbert space is going to factorize into HA times HB times HC, it's pretty clear that these modes A that we are talking about were modes defined by integrating the field on outside the horizon. The modes A tilde were defined by integrating the field behind the horizon. And therefore, it's reasonable, in addition now, to say that A and A dagger act within HA, and A tilde dagger act within HB. Okay. Then we're going to make one more assumption, which is that the early Hawking radiation is captured by HC. Okay. So the way we are thinking about this is that we have a black hole. The black hole has actually spent some part of its life, and it's emitted some Hawking radiation. That Hawking radiation has gone far away from the black hole. It's not close to the black hole in any sense. And because it's gone far away from the black hole, that Hawking radiation is now captured by the Hilbert space, which is HC, which is somehow capturing the degrees of freedom, which are far away. Okay, so that's the other assumption that we're going to make. Okay? And I emphasize that, some of you might be thinking even now, while we make these assumptions, that, these assumptions are not being made very precise, and, they're a little sloppy, but this is what it is, and this is how these paradoxes were formulated. And the question is, and that we'll need to examine later, is whether sloppiness is somehow a fatal problem for the paradox, or whether somehow, it's just the physicist sloppiness that we are able to get away with. I see that there are some questions right now. Is SBH a dynamic quantity? Yeah, thank you. So the idea, so there's a question in the chat which says SBH is a dynamical quantity, so this dimension of the effective Hilbert space is also changing. No, actually, so what we want to do is we want to say, we started with some black hole, or we are looking at some ensemble of black holes which have some given energy, and we are formulating the dynamics within e to the SBH of that. So this e to the s, actually that's a good question. This e to the SBH is the entropy of the black hole that we started with, and that is the space, or the dimension of the space within which we are formulating dynamics. This SBH changes in that, the black hole becomes smaller, and the degrees of freedom move from one part to the other. But the dimension of the full Hilbert space always remains e to the s. And in fact, that's the next thing I'm going to say. Okay. Are there any other questions?
There's actually a raised hand by Monica, I think.
Yeah.
Maybe.
Go on, please. Yeah.
Sorry, I had actually pretty much the same question. So can I think of this? So basically, even though there's an infinite number of states, if I sort of fix a maximum energy or a maximum entropy at which I want to work, then that defines sort of a well-defined finite size Hilbert space, large but finite size. Is this a correct way to think about it?
Yeah, I mean, in flat space, even that would not be true, because you would have soft degrees of freedom, and so you would have to worry about infrared cutoffs. Yeah, so
yeah, so I'm putting so I imagine I was thinking about ADS and global ADS, where I put my dual theory on finite size, so I can regulate infrared effects, and then I put a maximum cutoff on the energy, so I can just chop off also.
It's actually trickier than that, because even in global ADS, these black holes never dominate the ensemble. So, if you just put a cutoff in the energy, the dominant phase will just be gravitons with the same energy, just a gas of gravitons. And that's because the Hawking radiation has more entropy. So somehow you have to have a finer definition of the ensemble. You have to find a way of locating, even in ADS, which are the states which correspond to black holes and which are the states which correspond to a gas of gravitons. So one has to somehow define the ensemble of small black holes in some nice way, which, as far as I know, I mean, there have been some efforts which have been made, but has not been done very precisely.
And does this also limit what I can do to this black hole? Like I cannot punch it too hard because I might get out of the Hilbert space.
Yeah, I guess. You're right that, in some sense, you're within a larger Hilbert space, so you don't want to make operations that take you totally out of the Hilbert space. So that's part of this assumption that, yeah, we are working somehow. There's some. I mean, we believe in it. Probably reasonable assumption that you have this ensemble of small black hole states, and within that you can do like various experiments. You can define questions of correlators or quantum information and so on, without having to worry about the fact that there's a larger Hilbert space within which they're embedded in, which is the gas of gravitons. For these evaporating black holes, they're always embedded in the larger Hilbert space because the entropy of the Hawking radiation is always larger, just because of the infinite volume. And so somehow we want to focus on a smaller subsector, a smaller ensemble of states which are black holes. And you're right that restricts some of the questions, some of the things we can do.
Okay, thanks.
Okay, thank you. Okay, so now, actually this is related to some of the questions that people asked. You see, let's consider an old black hole. Okay, so consider, and this will be important. And what old means is that it has more than half evaporated. Okay. So that's what old means. So old actually means something precise. It means that it is more than half evaporated. And when I say more than half evaporated, I mean that the entropy has come down to less than half of SBH. Now, because we are formulating this within this effective Hilbert spaces, what we would like to say is that in this setup, the dimension or the degrees of freedom within this Hilbert space HC, or the effective dimension in some sense of the Hilbert space HC, is somehow larger than the Hilbert space of the complement. Okay. And the reason I write much larger here is because I remind you, so this is the complement of HC. And the reason I write much larger here is because I remind you, once the black hole has gone to has evaporated by 0.51, then already the dimension of HC becomes e to the 0.51 s, and the dimension of HC bar is 0.49 s, and the difference between these two is 0.1 s is e to the 0.1 s, and e to the 0.1 s is a huge number. And that's why, even if the black hole has just evaporated by a little bit more than half, you already have this inequality where the dimension of HC is much larger than the dimension of its complement, and e to the s by 2 is sitting in the middle. Once again, let me just remind you, so you keep track at all times of what HC is. So HC is this degree of freedom, is a space that's far away. Okay, so HC has become very large for an old black hole, and that's because most of the black hole is evaporated, and so the Hawking radiation has gone into HC, and it's much larger than its complement, which comprises A, B, and also the remaining pink region inside. Okay, very good. But now if this is the case, then we are actually, is a question? Yeah.
Sorry, very quickly. Is that S the one that we call SPH before? So
yes,
the entropy at the beginning. Thank you.
Thank you. Yes, it is SPH. Thank you. Yes. Yeah, I hope I've been careful with that. Yeah, but that's SPH. Okay. So now if we do this, then remember this is precisely the setup that we had at the end of the last lecture. Where, we had two spaces, and we said one space is much bigger than the other space in its complement. And this is precisely the setup that we said we can find maximal entanglement. We also discussed this a little bit at the beginning of this lecture. Right? So this means that for A1 and A2, remember A1 and A2 act not on HC, but they act on the complement of HC, right? They act on the complement of HC because A1 acts on this region which I'm calling A, and that is in the complement of HC. The complement of HC is bigger, but A1 and A2 act on the complement of HC, somewhere in the complement of HC. And therefore, this means we can find C1, C2, find some C1, C2, which have the property that if you define CAC as being A1 into C1 plus C2 plus A2 into C1 minus C2, then you will have a maximal violation of, or you'll be close to saturating Cyrelson's bound. Okay. I emphasize, as we said at the beginning, that it may be that there are corrections. Maybe you're not quite at 2 root 2. Maybe you reach only 2.8, but that's fine. The point is we can go quite close to 2 root 2. And this arises just from assuming that, you had a generic initial state. You have this big Hilbert space. The Hilbert space is factorized. There are more degrees of freedom in C than in its complement. Therefore, for every operator that acts in its complement, its partner is almost certainly in C. And therefore, for these operators A1 and A2, we expect that the partner is in C, and that's C1 and C2. Right? Very good. But if that is the case, you see that now we have a paradox, because earlier we found that the expectation value of CAB was greater than 2. And now we have found that the expectation value of CAC is 2 root 2. And remember, we had this beautiful inequality. The beautiful inequality told us that the squares had to be less than 8. This had to be less than or equal to 8. And clearly, the inequality is being violated, because on the one side, we find that CAB is larger than 2, which reflects the fact that the modes on outside the horizon are entangled with the modes inside the horizon. On the other hand, we have the fact that CAC is almost 2 root 2, which reflects the fact that the modes near the horizon are entangled with modes which are very far away. And in fact, CAC square is almost 8 by itself. So it's, as we discussed in the class, it would mean that AB should have no correlation. So should have almost no correlations. And here we are finding not only do they have almost no, not only do they not have almost no correlations, in fact, they are themselves entangled in that the correlations that they have exceed the maximal allowed classical value. And so you see, for some values of beta omega, you would in fact find that CAB square plus CAC square, if all these calculations are correct, is actually 16. And that clearly violates this quantum information inequality that you have. Okay. I want to emphasize a few points, and then we will discuss tomorrow more about this paradox, but let me just emphasize a few points. The first point I want to emphasize is that this paradox is different from the Hawking paradox, because this paradox makes reference to the interior. It makes reference to the interior and not just to the exterior. This paradox is not just a paradox about, oh, you know, outside we are finding that the entropy is just growing and growing. This paradox is not saying that. This paradox is saying that, you know, when to preserve a smooth horizon, you need to have entanglement across the horizon. And that tells you that A and B together have to be entangled. You know, okay, you know, A can have some degrees of freedom. Maybe A looks thermal by itself and so on. But A and B together have to be entangled at all times. And that's where this paradox makes reference to the interior. And secondly, this is an order 1 violation. And this was, in fact, Mathur's main point, is that this is an order 1 violation. And because it's an order 1 violation, you know, just to emphasize once again, we are finding that psi into this expectation value is, you know, this expectation value is -8 is like order 1. Because we are finding that it's exceeding 8 by an order 1 amount, the claim is that maybe small corrections will not help you. You know, in this lecture also I said, you know, things don't factorize, and you know, we haven't been careful about quantum gravity corrections and all these correlators. We have these order epsilon terms and so on. But the whole point of setting up this paradox was to say, you know, fine, you know, maybe you have all these order epsilon corrections, and you made such a big deal about these exponentially small corrections, which we also did. And you said, well, you know, that will restore unitarity. But now what? You know, now you have a violation which is just order 1, and no, you know, no order epsilon looks like it will help. Okay, so this is the essential way in which this paradox is different from the original paradox that we formulated, in that we have some quantum information result which we proved, and then we made some other set of assumptions. We did some calculations in effective field theory. We used some general results from quantum information, and then we found that we are violating some quantum information result about the monogamy of entanglement by an order 1 amount. And now, you know, Mathur's point was, you know, you said e to the minus s by 2 corrections will help. Now show me how they'll help. You know, if you're at 16, how can e to the minus s by 2 ever get you down to the sum of the squares being 8? Okay. So these are the 2 salient features of this paradox. This paradox, when it was originally formulated, as I said, was not formulated in terms of Bell correlators. It was formulated in terms of the strong subadditivity of von Neumann entropy. In the beginning of tomorrow's lecture, I'll try and describe that formulation briefly, because that's also nice, and that's how much of the literature treats it. But here, you know, we see that these things are just totally free of UV divergences. Everything we computed, they're just some numbers we computed, and you know, it clearly looks like we have something which is violating you know, the monogamy of entanglement, and so that is the monogamy paradox. So this is actually a good place to stop. Tomorrow we will discuss first, as I said, the issue of how this paradox is formulated using the von Neumann entropy, and also what the fuzzball and firewall resolutions to this paradox were. They're similar but not exactly the same, and so tomorrow we'll discuss that. But this is a good place which summarizes what the paradox is. So I'll stop here and we can take questions.
Okay, Suvrat, there's one question in the chat. He's asking, can you please repeat the argument for entanglement between modes in A and C Hilbert spaces?
Yeah, okay, thank you. You see, the modes in A and C Hilbert spaces was based on this quantum information result that we proved in the last lecture. It was the fact that if you take a generic state in this kind of a situation, where the dimension of HC is much larger than the dimension of HC bar, that, you know, effectively there is, you know, more of the system is in HC than it is in its complement. Then if you take any operator that acts on the complement, and for a generic state of this kind, the partner of the operator, and by partner I mean the operator with which it is entangled, lives in HC. Okay? So if you take any operator in HC bar, its partner lives in HC, in that if you can find pseudospin operators in HC bar, you can find operators in HC, so that Cyrelson's bound is close to being saturated. Okay? So that was the general quantum information result, which holds for generic states. Now we see here that when the black hole has more than half evaporated, when you have crossed half, and by half evaporated, it means something specific. It means that when the entropy has decreased to less than half of its original value, you are in this setup where the dimension of HC, or the degrees of freedom in HC, are much larger than the degrees of freedom in HC bar. And therefore, for these operators A1, A2 that you can find, that you can write down in HC bar, you expect to be able to find operators which are C1, C2. That's what this slide says. So that CAC is 2 root 2. Okay? And this is from the general quantum information result. Okay? So this is from the QI result that we proved at the end of the last lecture. Okay? So I have not found for you what these operators are. I want to emphasize that I wrote down an expression for A1, A2 in terms of field operators. Okay? I did not write down an expression for C1 and C2 in terms of field operators. I just said they must exist based on generic quantum information arguments. And in fact, this will be important later, because we will find these C1, C2 have to be very complicated, and then that will lead us into a possible resolution. But for now, I just, the point is that it's an indirect argument that says, they must exist, and therefore there must be some operators C1, C2 that are entangled with A. Okay? I hope that answers the question. Great. Are there any other questions?
So I think my question, I think you kind of just answered it in the last sentence that you said, because one of the things that you needed to do to ensure that the order epsilon corrections were controllable, that they were small, that you can't really consider operators that are too complicated, that they have very, very high point correlation functions, because then right. The coefficients of the order epsilon term might be very, very large, and then that might itself be so is the point that you were making is that these operators C that are entangled with the operators A1, these C1 and C2, they could in principle be incredibly complicated operators and actually give you order 1 corrections?
Yeah, so C1 and C2 will be incredibly complicated operators. Actually, the order 1 corrections, there are different resolutions, but the resolution I'll try and argue for a little bit later, at least the one I prefer, is that, the commutator of C and B, which you thought was small, will actually turn out to be large, in that, you thought that you could, it's the fact that you said the Hilbert space is factorized, which in particular meant something precise. It meant that the commutators of operators on different parts of this diagram A, B, and C is small. And that is indeed true for simple operators. And A and B are simple operators, and so the commutator is suppressed. But the C is an operator that you kind of picked out by saying, oh, there's a quantum information result that tells you it exists. And it exists, but the quantum information result doesn't tell you how complicated it could be. And if it's very complicated, it might have a large commutator with B and A, and that could invalidate the problem. And that could invalidate the result. This result that we have here obviously doesn't hold unless AB and AC commute. So if B, for instance, doesn't commute with C, then of course the result doesn't hold, and so that indeed is a loophole which will be important. Exactly.
Yes. Okay, thank you.
Excuse me. I have one question. Can you explain a little more why this formulation is better than the one involving strong subadditivity of entanglement entropy or von Neumann entropy?
It's a little bit so I mean, okay, so that's also perfectly good, that gives you the same physics. It's a little bit better because the strong subadditivity is the von Neumann entropy is a UV divergent quantity. So I'll say this again in the beginning of tomorrow's lecture. You could have defined this by saying, look, let's look at SAB, SAC, and let's look at these von Neumann entropies of these regions on this slice. But now this SAB is not something that's well defined it's not even well defined in a quantum field theory. You know how to regulate it, but it's something that looks like it's particularly ill-defined in the theory of gravity. And you might worry that given that it's UV divergent, maybe as the black hole evaporates, how do you know that the coefficient of the UV divergent term doesn't change, or something else of that kind doesn't happen? So when you compute von Neumann entropy, you're always computing infinities in a quantum field theory. You're comparing infinities to each other. And that's the reason this is a slightly better way to formulate it, I think, because there are no infinities. And at least one part, which was the CAB part, you could just compute clearly within effective field theory. And you get some number, which is between 2 and 2 root 2. And for the other part, you say you're getting 2 root 2. But there's no infinity anywhere inside. Whereas for SAB and SAC, there are infinities inside. And I mean, I certainly remember when these paradoxes came about. people did worry a lot about these infinities and how you define these quantities. But for CAB and CAC, there isn't really any, at least for CAB, there's no issue of how you define it in gravity. It's a 2-point correlator. You define it just, as long as you can define quasi-local operators, you can define CAB. And, so there isn't a question of, these are in slightly cleaner systems because they're not UV divergent and because they involve 2-point correlation functions, which you think are still well-defined. For Neumann entropy is a more subtle quantity. I hope that answers the question. Does that answer the question?
Yes, perfect. Thank you.
Okay.
I also got a question. This is regarding also the factorization of the Hilbert space. I think we're coming to this in the coming lectures, but is there a possible way in which you can create some sort of setup in which these three areas A, B, and C do actually factorize? For example, if it's, I mean, if we just see it as a quantum field living on a slice without gravity, then it does actually factorize, right?
Correct. So yeah, so indeed, so that would be the paradox. So that's what we will have to argue. And indeed, the assumption when these paradoxes were made was precisely this. It was that, let's take a very big black hole, right, which is the size of the Milky Way. The horizon is the size of the Milky Way. And then, let's go very far away from the black hole, and we are free to do these kinds of thought experiments. And then, why shouldn't we be able to think of quantum fields that propagate in curved spacetime? And then why shouldn't we be able to talk about factorization, particularly since we are getting an order 1 violation of the monogamy inequality? So, why should all of these things matter? Just to say, I mean, we'll discuss this in the coming lectures, but the point is that it's about the complexity of these operators C. And, the commutators of operators inside and outside are suppressed by roughly the energy scale divided by the Planck scale. So they're suppressed by that's the entropy of the black hole. And these operators C, if they start having S-point insertions, like if they look like a field to the power S, then that commutator invariably becomes large. So you could try and say, I'll take like G Newton to be very weak, very small. But if you do that, you raise the value of S and you increase also the complexity of these operators C1 and C2. So, that's where the potential loophole is. I'm not saying that I'm giving you right now a resolution. And indeed, people could say, and people do say that, let's just think of systems which are very far away and a very big black hole. And, it's clear that I can do local experiments here and, it doesn't affect something that's happening somewhere else. And so why can't I think effectively in terms of factorization? So that's the argument for factorization. And the counter argument is that, look, that C1 and C2 will become very complicated, which we'll discuss in detail. But you're right. It is a priori, a plausible assumption which you could have made. And that's why, this is an interesting paradox. I mean, it forces us to confront this issue of factorization.
All right, thank you.
Yeah, okay. Great. Yeah, other questions, or?
I had a bit of a basic question actually related to my previous question. I'm still always a bit confused how you create entanglement and how you can destroy entanglement. Can you maybe comment on that?
Sorry, where did we create and destroy entanglement in this discussion?
No, not necessarily in this discussion, but in general, what are ways to create entanglement and what are ways to destroy entanglement?
Oh, okay.
Aside from
okay, so yeah, you could, if you take two systems and you allow them to interact, you would entangle the two systems. If you now take one of the systems and you make it interact with a third system, you would create entanglement between this system and the third system, and therefore you would break the entanglement between the two. I mean, to take a simple example, if you had a qubit, two qubits, you could make them interact so that you prepared an EPR pair, and then you could measure one of the qubits. If you measured one of the qubits, that means you make the qubit interact with some measuring apparatus. Now you've broken the entanglement because now you've collapsed the wave function, and what that means is that the qubit that you had in your lab is now entangled with your measuring apparatus. It's no longer entangled with the other qubit that was sent somewhere else. So it's by processes of interaction that you would generate entanglement and destroy entanglement.
But any interaction, because you gave measuring as an example, like any interaction would also be able to destroy entanglement or transfer entanglement, so to say.
Yes, it will transfer entanglement, exactly. So there was some problem with the connection, but when you said, interactions will, as you say, transfer entanglement. So, they could make two things entangled, or they could make one thing entangled with the third thing, in which case the original entanglement would be broken. Maybe I'm not understanding the question.
No, essentially it's a very basic question.
Okay.
But I was always a bit confused on that, so it's clear. Thanks.